With the local extremum theorem, we saw that local extrema can only occur at either critical points or boundary points of the domain. So that limits our search for these extrema to only points where either the derivative is undefined, the derivative is equal to 0, those two cases constituting the two ways in which a point can be a critical point, or the endpoints of the domain. So since a global extremum must always be a local extremum, this gives us also a way to search for global extrema. So basically, to find global extrema, we basically look at all the possible candidates. So first, locate all of the critical points. So again, there could be a discontinuity in the function at a given point. There could be a sharp corner in the function or an edge, or the derivative can equal 0. So the three ways in which we can get a critical point is if there's a discontinuity, because if the function's discontinuous, it cannot be differentiable, and therefore the derivative is not defined. There could be a sharp corner, which indicates that the derivative is not defined at that point, or the derivative can equal 0, so the tangent line is horizontal. So I'll just say, or a horizontal tangent line. Okay, so we look at for all the critical points, and then we locate the boundary points. If any. And basically, these are all of the suspects for the local or global extrema. So any local extremum has to be in one of these points that we've found. So if we know the global extrema exists, so the function has global extrema. So in our previous video, we saw that it's not always the case that a function has a global extremum. We showed several different ways where a function could not be in possession of a global extremum. But if we have a continuous function defined on a closed domain, then it must have its global extrema. So the main way in which we would be able to guarantee that the function has a global extremum is the extreme value theorem. So in other words, the function has to be continuous and defined on a closed domain. So if these two are satisfied, then we know that the function has global extrema. If those two are not satisfied, it may or may not. It may have a global maximum but no global minimum. It may have a global minimum or no global maximum. It might have neither global minimum or maximum, or it might have both a global minimum and a global maximum. So, but the extreme value theorem says in the single case where you have a continuous function and your interval is closed, so it's defined on a closed interval, then the function always has a global maximum and a global minimum. So if we know that the function has these global extrema, otherwise exercise caution, we can simply evaluate the function at each point uncovered by items 1 and 2, and then select the greatest and least as the points where the global extrema occur. So in other words, if we know that the local extrema have to be either at the boundary points or at the critical points, so we round up all of the boundary points and all of the critical points. Supposing we have a continuous function defined on a closed domain, from the extreme value theorem, we know that it has a global maximum and a global minimum. So it has to be one of these points that we rounded up. Now, we might be rounding up points that are not local extrema, but that's okay. We'll keep those along for the ride. And then we just evaluate the function on all of those points, the critical points and the boundary points, to find out where the maximum points really are. So that will be able to show us when you have the maximum. So just a brief picture of what this looks like. So here's a finite domain. So it's defined on a closed interval, so it includes the endpoints. So the x interval goes from, like, say, here to there. We have some critical points, critical point, critical point. This one works out to be a local maximum. That one works out to be a local minimum. This boundary point is a local minimum. And this boundary point up here is a local maximum. And let's actually, even though this is a nice smooth curve, let's jazz it up a little bit. This guy goes up like that, and then it comes down like this. So then, in this case, we have another critical point right here, local minimum, and then we have another critical point. Now this one's different than the previous three critical points, in that it doesn't have a horizontal tangent, but the derivative does not exist there because we have this sharp edge right there. So it's another critical point, and that one is a local maximum. So since it's a continuous function, so even though it's non-differentiable at this point, the function itself is still continuous, I know that it has a global maximum and a global minimum. And in fact, they're easy to spot. This point right here is the global maximum, and then this point down here happens to be the global minimum. So this output value is less than any other output value on the entire domain. And then this output value up here is greater than or equal to any other output value on the entire domain. So you can see that we have the continuous function on a closed interval, and our global max and global min indeed are both, in this case, both critical points. It's easy to imagine if it was a boundary point, because if this boundary point here was lower, then that would be the global minimum if it had an output value less than that. So it's just the relative position of everything. So basically, locate the boundary points, take the derivative, set it equal to 0, so that will give us this point, and that point. Derivative is not defined at this point, so we include that too. And then we just test the output values of these 1, 2, 3, 4, 5, 6 points. The largest output value is here, so this point is the global maximum. The smallest output value is right here, so this point's the global minimum, and that's basically the procedure. Without actually working out an analytical example, that's a basic procedure for finding the global extrema.